Swayam Prabha. Digital India. Educated India.
Welcome to the 6th lecture of module 5, that is on wire beam additive manufacturing. So, our today's discussion will be covering these topics. We will start with the classification of the wire additive manufacturing and particularly focus today on wire beam additive manufacturing. And then the focus of today's lecture will be on the process utilizing the electron beam. So, as electron beam is going to be the focus for today, these are the topics I will cover for electron beam, that the virtue of electrons, electrons emission, electron beam gun, electron optics for focusing the beam, need for vacuum in this system, electron beam based wire beam additive manufacturing systems, the material beam interaction, the challenges associated with this system and other systems for EB WBAM. So, this is our classification, as we are not going to discuss about the polymer wire and the wax wires. We will discuss only for metal. Then further removing these material side, this will be the further classification for metal wire additive manufacturing. We have already discussed about the arc completely. We have discussed about TIG, we have discussed about MIG, we have discussed about plasma as well. Now our focus is today when the energy source is the energy beam. So, that is why we are eliminating all the materials and just focusing today on the metals. If metal is used and material is flowed continuously or material is deposited based on the drop on demand, whether the machine is using serial kinematics, parallel kinematics or the hybrid kinematics, the energy source will be energy beam. We have already discussed about the arc based systems where MIG, TIG and plasma was used. Now our focus will be on energy beam. There are two possibilities for energy beam. The first is the electron beam and the second is the laser. So, our today's focus will be on the electron beam based additive manufacturing systems. Of course, there will be no possibility of using the support mechanism, and if we want to eliminate the need of a support mechanism, multi-axis kinematics will be used. So, the virtue of the electrons. If you observe an electron, its mass is very less. Its mass is around 9.1 into 10 to the power minus 31 gram. The charge which usually an electron carries is of minus 1.6 into 10 to the power minus 19 coulombs. Then being such a lightweight particle and with very low charge, how it is really generating the energy on the substrate? So, basically the energy comes from the kinetic energy available with the electrons, meaning to say it comes from its high speed. So, the virtue of electron is the kinetic energy, and by utilizing this kinetic energy only, it creates it or it transfers the energy into the substrate. So, it is not the weight but its velocity that can be increased to 2/3 of the speed of light, and that generates the kinetic energy. If you observe this particular graph, you can see that if I keep on increasing the accelerating velocity, the electron's speed can be close to the speed of light as well. I'll just show you this video where you can see the different lines, right? These are created by scanning the electron beam, but you will be surprised to know there are not multiple beams here. There are only single beam which is writing with such a high speed that we are not able to see it as a single beam, while it looks like multiple beams are moving on the bed. So, this ability of electron beam to scan the area with a very high speed, and again the particle's velocity of a very high speed can transfer a very high amount of kinetic energy into the substrate. So now let us discuss that how can we generate the electrons from a particular material. There are 5 different methods by which we can be able to extract or emit the electrons from the object. So to emit or produce electrons from any solid state material, minimum energy which is equal to the work function is required to break the potential barriers and bring out these electrons out. So for example, if we talk about the thermionic emission, in the thermionic emission we used to have a metal, and when an appropriate amount of heat is supplied to this metal, it start emitting the electrons. The Richardson law for thermionic emission is given here, and it can be used to find out the current density emitted from the emitter surface. So for example, the current density J will be equals to A, which is a constant, into T to the power 2 exponential minus 11600 W divided by T, where W is the work function of the emitter and it depends on the material. Like for example, if I talk about the tungsten, the value of this W is 4.52 electron volt, and T is of course the absolute temperature of the emitter. As you can see from this formula itself, if my T will increase, this whole term will decrease. As a result, this function's value will increase and my current density or the electrons emitted from the surface will increase. So this is called as thermionic emission. Each and every metal, when it absorbs a certain amount of heat, will definitely generate some number of electrons, but how to generate the certain amount of electron from the surface of the metal will depend on the energy we are giving to it and its property, which is called as the work function. The another way of generating photon is by providing the photon energy. Photon energy is nothing but our laser beam, which used to have the photon, and these photons, when they strike to the substrate, generate the heat, and then it used to generate the electrons from it. So directly we are not giving any heat to the surface, but instead we are giving the photon energy, and that results in emitting the electrons from the surface. Or we can use another electron beam gun itself, which produces the secondary electrons, and they become the reason for generating the primary electrons from the metal. Or we can have the ferroelectric material. We know that in the ferroelectric material, the bipolars are aligned in an appropriate way, and when a potential difference is given to this, the one side of the ferroelectric material will start emitting the electrons, and the electrons will go towards the positive terminal. And this is how also you can also generate electrons from a material itself without giving any external heat. So the fifth one is the plasma, and we know that the plasma is consisted of the positive ions and the electrons because of the ionization of the gas inside. Now our aim is to extract these electrons out of the plasma and leave the ions behind. So that is how you can generate electrons or extract electrons from a plasma, and it can be easily done by giving appropriate terminal voltage to it. If I connect the positive terminal at the bottom side, then definitely electrons will attract towards it and can be extracted from the plasma. For material processing such as welding, lithography, additive manufacturing, etc., thermionic emission and plasma emission are the most popular ones. So our focus for further discussion will be only on thermionic emission and the plasma emission. Now let us discuss about the electron beam gun. As I have already mentioned, our focus is going to be either on the thermionic emission gun or on the plasma emission gun. We are going to discuss here, as our focus is going to be either on the thermionic emission gun or on the plasma emission gun. That is why these two systems are shown here. This one is the thermionic electron beam gun and this one is the plasma electron beam gun. Now in a typical thermionic electron beam gun, there will be a cathode on the top, and when we give sufficient heat to this cathode, it will start generating the electrons. As it will start emitting the electrons, these electrons will be available at this surface of the cathode. Now we need something to pull these electrons out of the surface of the cathode. So for that, we used to give a voltage at a particular distance and also called as beam acceleration voltage. Now as the positive terminal is connected with this, and I am calling it as anode also, it will start extracting the electrons from the cathode, and these electrons will go with a high velocity. It will depend highly on how much potential difference you are giving. So now your electrons have obtained some velocity and now they are traveling in some direction. But as these electrons are closely packed with each other, they will start repel to each other because of the same charge available with each and every particle, and your beam will become diverged. Now it will be important for us to focus this beam further in order to obtain the desired spot size on the bottom. Therefore, a focusing coil is usually used. This focusing coil is electromagnetic coil, and it gives appropriate amount of force to these electrons, the moving particles, into this magnetic field. We know that as per the Lorentz law, when a charged particle moves into a magnetic field, it will feel or it will be subjected to a force, and that force will be utilized here to focus the beam further. Also, there are some deflection coils available after the focusing beam, and these deflection coils are usually required to give minor deflection into the electron beam which is focused at the bottom. However, the major deflection between, or the major relative velocity between the spot and the workpiece is obtained by the motion of the workpiece. Where on this side what you are seeing is a plasma electron beam gun. In this case, we used to have a hollow cathode. As this is a hollow cathode, inside there is a plasma. Now plasma can be generated by different means. You have already seen in the case of plasma gun, where the inert gas, when it is subjected to heat, it got ionized and produced ions and electrons. Now assume that this type of plasma is already available here, and our objective is to pull the electrons from this plasma, and let us leave the ions, those are the positive charge particles, behind. So to pull these electrons from this plasma, we will apply a voltage difference, and this voltage difference is applied to an anode available here. Now due to the positive terminal of this particular part here, that is anode, it will pull the electrons from the cathode. So this energy, so this voltage is called as the discharge voltage, because it is just sufficient voltage to pull the electrons out of this chamber of, or the hollow cathode. Once we have obtained or we extracted the electrons out of this hollow cathode, now our aim will be to give them sufficient velocity so that when they strike to the substrate, can produce sufficient amount of heat. Now for that, there is another electrode is used which is called as accelerating electrode, and that is further connected with a terminal negative to positive here. As now the potential difference is to give the acceleration to the electron beam particles, that is why I am calling it as V acceleration, the voltage required for accelerating the particles. Now these particles, those are available here, will go with a very high speed, and they will move towards the substrate. So this is a typical architecture of a plasma electron beam gun, and this is a typical architecture of thermionic electron beam gun. So you have seen the function of an electron beam gun is to produce, focus and deflect the electron beam as per the requirement. The electron beam gun which is used in additive manufacturing system are, I have already mentioned, could be the thermionic gun or plasma gun popularly. Like the RCAM, which is a powder bed based technology, we will discuss about it later on, and SIAKI, which is a wire based technology for EB, uses the thermionic electron beam guns, while the X-beam, uses a plasma electron beam gun. So let us now make a comparison between the thermionic gun and the plasma gun. Usually the current density we obtained in the case of thermionic gun is of range of 1 to 10 ampere per centimeter square, while in the case of plasma gun it is 1 to 10 to the power 2 ampere per centimeter square. This is because in the case of plasma we are already having the ions and the electrons available with the inside the plasma, and our aim is just to extract these electrons through a tiny orifice. As we are having a tiny orifice, the density of electron is restricted to that area, and as a result your electrons available per unit area or the current density, that is ampere per unit area, will increase as compared to the thermionic based system. Also, the acceleration voltage which is required for the thermionic gun is of range to 1 to 150 kilowatt, while for plasma gun it is quite low and 1 to 30 kilowatt only. Also, a high vacuum is required for thermionic guns. This is because our cathode, which is a metal, is usually at a very high temperature. Now if the vacuum will not be maintained inside that, very high vacuum will not be maintained inside that, then there will be chances of this cathode to absorb some of the molecules available in the environment and may get oxidized, and further its life will reduce. But in the case of the plasma, there is no such metal available at very high temperature which is subjected to wear. Therefore, low vacuum is sufficient enough for plasma. Both the case, vacuum is definitely required, and I'll come to the point why vacuum is required. But in the case of the thermionic gun, it is required more, the high level of vacuum is required, while in the case of plasma based electron beam gun, the vacuum is not really of that level. On the other hand, the life of the thermionic gun is low, that is around 50 hours, while in the case of plasma the life of the gun is quite high and may go up to 100 hours. This is again because of the life of the cathode only, because this metal piece is at a very high temperature and subjected to definitely a high wear rate. Then we'll come to the cost. Due to high vacuum, of course the cost of the thermionic gun is quite high, while the plasma guns are quite cheap. The application for both the guns is like melting, heating, machining, welding, and of course the additive manufacturing. So now let us discuss about how we focus the electron beam which is extracted from the cathode or from the plasma orifice. Now in most of the electron beam gun used in manufacturing, electrostatic field is used for the extraction of the electron and acceleration of the electron, but a magnetic field is used for focusing, deflecting, and correcting the beam shape. A schematic of such type of electron beam gun is shown here in this figure, and also the component of the Lorentz force are given in this equation that will be used for focusing. So from cathode to anode, focusing is done by electrostatic force, and from anode to required area it is done by the electromagnetic coils. So basically, for example, this is your cathode, it is emitting the electrons, right? Like I already mentioned, these electrodes will be bunched around the surface of the cathode. Now we need some external mean to extract these electrons from here, and that is usually done by the electrostatic medium. Hence, if I give a potential difference, that is electrostatic way of extracting the electron from the cathode, the electrons start coming with a high velocity towards the anode, and then they come very close to each other. When the electrons are coming very close to each other, we know that all the particles are of same charge, they will repel each other. As a result, after focusing, due to the electrostatic focusing, they will again start diverging. Now we have to make sure that these electrons come together and form a very tiny spot at the bottom, and that is usually done by now electromagnetic focusing. So if you observe this equation, the force acting on the electron is given by two components. The first is the electrostatic component and the second is the magnetic component. Due to electrostatic, which is applicable in this region only, we accelerated the electrons and they are coming closer as well and hence focusing also. But due to this one, which is F equals to V cross B, this force it utilized to further focus the beam in this region which you are seeing here. So what happened? If there is a particle, right, it is moving with the velocity v, and now assume that there is a magnetic field B in this direction. Now let us apply the right hand side rule. Put your fingers towards the velocity and cross it towards the magnetic field. This will be the direction of the force on the electron. Hence, this will be the direction of the force. So now you can see if there is a particle over here, right, if I appropriately give the magnetic field to this, then this particle will be subjected to a force F and it will make sure that this particle will move toward the center. It will make sure that this particle will move and hence follow this trajectory. It will happen similar way for this particular particle also, and there is another magnetic coil here and that will give the magnetic field in another direction, hence this particle will move in this direction. So based on appropriately giving the force to these particles, those are going to defocus, will further get focused at a particular point. And that is how we do focusing of these electron beams. A typical focusing coil used for generating the TEM is shown here. Now there is a question comes that how far it is going to be focused, and that is called as the image distance or the focal distance. The focal distance can be usually obtained by this formula. It says 1 upon F equals to pi e square divided by 16m E naught A B naught, where E is the charge of the electron, m is the mass of the electron, A is the width of the focusing coil. So all these three parameters are fixed. We cannot change in a particular gun at least these three parameters. Now let us talk about the variable parameters here. They are B naught, the magnetic field, and the accelerating voltage. So in other words, if I write this equation in a simplified manner, I can definitely observe that the focal length is directly proportional to E naught and the focal length is inversely proportional to B naught, that is the magnetic field, and it is like this. So now let us try to see if I increase the acceleration voltage. So if I here increase this acceleration voltage and give more voltage to accelerate the particles, what will happen? Their focal distance will definitely increase. Means they are going to be focused at a very large distance. This is because the particles are having very high velocity and they are going to travel a very long way in their path, and the focal point will keep on increasing if I keep on increasing this velocity, and this velocity is of course increased by the accelerating voltage. Also, if I increase the magnetic field into these focusing coils, right, in these two focusing coils, if I increase the magnetic field, then of course my force acting to the particle will also increase, and as a result, instead of focusing at very large distance, they may even focus very quickly as well if I give very large force. Hence I can decrease the focusing length. Therefore I can say if I increase the magnetic field, my focusing length can be decreased. So this formula works very well and very helpful to obtain the focal point for the electron beam, which is having some constant parameters such as the width of the focusing coil, and of course E and M are constant. Now let us discuss why do we really need the vacuum. So vacuum is not like we obtained the zero pressure inside the chamber, but removal of the air at least. We should not have any other particles than the electrons inside the working chamber. Why? Because the electron should we need to focus the electron at a particular point. If there will be particles available inside, the electron may collide with that and scatter here and there, and you will not be able to focus these electrons at a particular location. Another is, we have to also prevent the oxidation of the cathode. If you are using a thermionic gun, definitely high vacuum is required, because otherwise the molecules available in the air will react with the high temperature metal piece, which is the cathode, and will erode it, or its life will definitely decrease. So there are different ways of doing for obtaining the vacuum of different level, like the rotary pump are used to obtain the vacuum up to 10 to the power minus 2 millibar. Then the root pumps are used to obtain the pressure up to 10 to the power minus 3 millibar. After that, the diffusion pump or the turbomolecular pumps are used to obtain the vacuum even beyond 10 to the power minus 6 millibar. Then the root pumps and rotary pumps doesn't really are helpful. So there are two reasons where we want to generate the vacuum. One is, we want to generate the vacuum where my cathode is, at least in the case of thermionic emission gun. In this region, I need a very high vacuum, because I cannot tolerate to have any particle inside this chamber, otherwise it will definitely react with my hot metal piece and it will reduce its life. Another vacuum can be divided as per the requirement into the working chamber. In the working chamber, again we require the vacuum, but if there are a few particles remaining, will not be as critical as it is required in the electron beam gun, at least in the case of thermionic emission. So now let us see briefly about these pumps. So the first is the rotary pump. This is the typical rotary pump which you are seeing here, and its cycle. The first cycle is the suction of the air. So as you can see, there is a spring loaded valve here. It keeps on rotating and keeps on sucking the air from this port inside it. As after its complete rotation, when this lever rotates completely, the transport phenomena occur. Now this particular chamber is completely filled with the air. At the same time, of course, simultaneously, when this will move like this, it will start sucking the air from the chamber also. But let us focus now transporting. Now this chamber is filled with the air, and now as this valve will further move, the pressure of the air will act on this particular valve, and this phenomena will be called as compression. When the pressure will reach up to a certain limit, this valve will get opened and the air will be removed from here, and that is the emission step. So this is how a typical rotary pump works. Again, the cycle will repeat itself. It will suck the air from this end, will transport to this chamber, and then it will compress it, and when the pressure will reach, it will remove it or push it away outside. Similar fashion, the root pumps work. In the root pumps, there are loops like you are seeing here. They keeps on rotating. Again, there are two chambers. One is this one and another is this one. This one is corresponding to the inlet low pressure, where from the we are sucking the air, and this is the outlet pressure corresponding to high pressure, where we are pushing this air away. It keeps on collecting the molecules, air molecules, and keeps on transferring it to another chamber and pushes outside. But when it comes to the extraction of the light molecules available in the air, these root pumps and the rotary pumps cannot really work very efficiently, and hence we will be requiring the diffusion pump and the turbomolecular pumps. So as you can see in this circuit diagram as well, rotary pumps and root pumps are attached in series with the diffusion pump. So let us first talk about the diffusion pump. These air molecules, those are light in weight, will get diffused with the oil particles and their weight will increase. As now the particles weight will increase, definitely the root and rotary pump will be helpful to extract them away. So this is a typical diffusion pump. These are the particles, air particles, those are having the light molecules, and there is a heating element on the bottom which is heating a chamber which is filled with the oil. As now these air molecules will go into this chamber, they will diffuse with the oil particles, and as they are going to diffuse with the oil particles or the oil vapor, the particles are going to become heavier and they will be easily now extracted with the root pump, by the root pump or rotary pumps. So this is how the diffusion pump work. But we can definitely use the diffusion pump in the working chamber, but it is very risky to use this diffusion pump in the electron beam gun site, because here these oil particles, if they are somehow remain into the electron gun chamber or the beam generation chamber, they may react again with the high temperature metal piece, that is my cathode, and may create further issues. Therefore, preferably there turbomolecular pumps are used. So this is a typical turbomolecular pump in which the light molecules from the air are getting extracted into a chamber which is consisted of the stator blades and the moving blades. We know that the provision of a stator blade is to provide the direction to these molecules towards the moving blade, and this moving blade will increase the velocity of these particles. Even though they are very lightweight particles, due to these moving blades their velocity will definitely increase and they will be able to suck up by the rotary and root pumps easily from this outlet. However, the turbomolecular pump has its own limitations and cannot work in all the orientations, while the diffusion pump can work in any of the orientation. That is why preferably diffusion pumps are used for the working chamber. Of course, they have to be aligned with the rotary and or the root pumps, and the turbomolecular pump aligned with the root pump or rotary pump are typically used for the gun chamber. So this is a system by Siaki. Here you can see that the big components can be made with a very high deposition rate. The electron beam is coming from the vertical and a wire is fed into the molten pool, as you are seeing here. They usually have two wires deposited simultaneously or alternatively into the molten pool. They uses the thermionic gun and have already tested the machine with several materials such as titanium as well. The processing of material is happening into the vacuum environment. It is very essential for metal to obtain very high material integrity in this case. Of course, they uses the multi-axis kinematics, as you can see here, a rotary axis and A axis along with the X, Y and Z axis on the top, in order to realize the overhanging features. If these axes will not be there at the additional two axes A and C axis, it will be limited to only realizing the prismatic objects. Those are visible only from the top. So the same is shown here, the schematic of a typical electron beam based system. So this is the gun from where the electron beam is coming and creating a molten pool, and in that molten pool we can feed the wire. And this is the schematic diagram of the same chamber. You see that there is a big chamber here and the part is attached with a rotary table. Rotary table used to give the appropriate tilt to the part in order to eliminate the need for support mechanism. They utilizes dual wire, wire 1 and wire 2 to feed into the molten pool created by it. That will definitely increase the deposition rate as well as to obtain the omnidirectionality. Now let us see how the material and beam interact with each other. So for example, this is your wire coming and from top there is an electron beam. As the electron beam will interact with the wire, definitely the wire will start getting melted. What is the desirable condition? If the wire melts very much far away from the substrate, the droplet will fall down. That is not preferable. Also, if the wire is not able to melt or increase its temperature sufficiently, it will plunge into the substrate and that is also not desirable. So the desirable condition is that this height h, where the droplet is generated on the wire or the tip of the wire, should be equal to 2r. That is the preferable condition. Of course, if this height is more, we will have the drop transformation. That is not critical but not really desirable. Most appropriate is when h is equals to 2r. But the critical is that h has to be greater than 2r. It cannot be less than. If it is less than 2r, then definitely my wire will plunge into it. My wire will plunge into the substrate. So typically, what kind of forces act on a droplet which is formed by melting the wire? Definitely, there is a gravitational force which acts in a downward direction. Then there is an electron beam pressure force, EB. So there is a beam coming from the top that will apply some pressure on this drop in the downward direction. Then there is a metal vapor jet force that is coming from the bottom. So if you see this one, this diagram, the vapor of the metal which is generated by the electron beam will pushes the droplet above. It will not allow it to fall down, and that is why this force direction VF is in upward direction. Then the surface tension force that will restrict the fall of the droplet onto the substrate, and it is represented here in this direction. So of course, it will be pulled by the periphery of the wire. So now let us have a balance on these forces, and as a result we will have the gravitational force Fg plus the electron pressure force, that is also downward, Fe, equals to Fv, the metal vapor jet force, plus the surface tension force, which is also the component of Fs is also acting in upward direction. So how much it is? So for example, you are feeding the wire at an angle theta, then of course its upward force will be Fs sin theta. So how do we calculate these forces? We know the gravitational force, it is easy to calculate, it's just mg. Now the metal vapor force can be calculated as F equals to the pressure of the metal vapor or the metal vapor jet pressure into the surface area on which it is acting, and we know that it is acting on depending on the radius of the jet. So for example, this is the radius of the jet which is applying the force onto the droplet, and for example the area of this radius of the vapor jet circle is given by Re, hence this area S will be equals to pi Re square. The pressure, the vapor pressure, can be given by this formula, and it says PV equals to 0.5 P naught exponential delta H T minus TV divided by RT TV, where TV is the boiling point of the base metal, delta H is the latent heat of vaporization, R is the universal gas constant, and T is the liquid surface temperature, where also P naught is the ATM pressure. All these variables are easily known to us, and we can find out the value of Fv, right? And then the value of Fs, which is the surface tension force, which is acting like I have already mentioned in this direction, and its component Fs sin theta will be in upward direction. So this sin theta component here is corresponding to the component of force acting in upward direction, and of course the surface tension will be the periphery of the wire, periphery of the cross section of the wire, which is nothing but 2 pi Rw into sigma, where sigma is of course surface tension coefficient and Rw is the radius of the filler wire. Now we have got all the forces. Let me put these forces back into equation number 1 to obtain the value of the critical radius, beyond which it will be a dip transformation and before which it will be a droplet transformation, and at the critical value it will be a perfect bridge transformation. So this critical radius, by putting all these forces back into this equation, will be equals to R equals to 0.405 P naught Re square, Re is the radius of the vapor jet circle, exponential delta H, which is latent heat, divided by R TV, where R is the gas constant and TV is the boiling point of the base metal, divided by rho L, where rho L is the density of the liquid, exponential minus delta H divided by RT plus 3 Rw, where Rw is the wire radius, sigma, which is the surface tension coefficient, sine theta, theta is the angle at which we are feeding the wire, divided by 2 rho Lg to the power 1 upon 3. So from this equation we can easily find out what is going to be the typical radius of this r. Once we know the value of r, we can easily obtain the value of this distance of the wire tip from the substrate. It should be at least 2r or greater than that. If it is greater than that, definitely the metal will be transformed in droplet form, and if it is equal to 2r, then the bridge transformation will occur. So preferably we should keep it as equals to 2r, the height. So our ultimate goal, which was to find out the value of this height of the tip of the wire from the substrate, h is going to be 2r, and we have already seen how to calculate this r. So the challenges associated with electron beam based wire beam additive manufacturing are listed here. The first is residual stresses and distortion, which was already discussed in the case of MIG based wire additive manufacturing, and it is going to be same here as well. The second is surface roughness or the surface finish. As the deposition rate is quite high in this process, of course we will be having more RA value or the very bad surface roughness in the parts prepared by this process. Of course, there will be a need for generating the support material, but as we cannot use the third material here, appropriate tilting of the substrate has to be done to capture the droplets appropriately. Another very important challenge is associated with electron beam is the vaporization of the alloying element material. So if there are some alloy available, it may evaporate one of the element of the alloy, and in that case that final product may not be having that element. Of course, the another issue is omnidirectionality, which is very much similar we discussed for TIG welding, where if you are feeding the wire from side and you are moving on a trajectory, sometimes you will find the side feeding, then it will become back feeding, it may become again side feeding, and then it may again become front feeding. So you have to maintain these feeding directions into the molten pool. Of course, for that there are two possibilities. One is dynamic adjustment of the substrate to maintain the omnidirectionality. It is already adopted for many electron beam systems, like Siaki is using it. You can see that their rotary table keeps on rotating. I'll show you that. Also, in some cases, I have found that the hollow cathode can be used. So these are the two systems for obtaining the omnidirectionality in electron beam based wire beam additive manufacturing. The first is coaxial feedstock surrounded by fusion source. So if I have multiple EB gun like electron beam gun 1, electron beam gun 2 and electron beam gun 3, and I am able to deflect these electron beams, because I can deflect them with a very high speed and form a small cone around the molten pool at each side, right, I will end up having a cone like this. Now the energy is available at all the position and the wire is coming from the center. As the energy is available now with me in all the directions symmetrically, I can move in any direction and process will become omnidirectional. Another way is to use the hollow cathode itself. Like for example, in the plasma electron beam gun, I have the plasma medium inside, and the orifice from which I am going to extract these electrons or discharge these electrons is having an annular shape. Now these electrons are having, or the electron beam is formed in an annular shape like this. If I take a cross section at a very high distance, maybe for example I am taking the cross section here for the electron beam, it will look something like this. It will not be having electrons at the center, but yes, as it goes down, definitely these electrons will keep on coming down, and if I draw a cross section at this location, it will be very tiny orifice remaining. I mean the very tiny space where there is no electron, and they further keep on coming down, 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 and further they got merged, right, at the location where the molten pool is created. At the same time, in this hollow zone, I can feed the feedstock, my wire. Now wire is at the center and it is surrounded by the heat source appropriately. So coaxial feeding of wire surrounded by the energy source will be now available with us, and now you can move in any direction. The process will be omnidirectional. The another possibility is by rotating the substrate. as you have already seen in the case of the Siaki system, there is a rotary table available. So what I can do, I can appropriately rotate my table in such a way that always a particular type of feeding mechanism is maintained. We have already seen this in the case of TIG welding in my last lecture. So the NASA is the first organization which developed the wire based process and called as solid freeform fabrication. This is the system developed by NASA. There is an electron beam gun here, and this is the chamber in which inside that there is a A and C axis, and of course the electron beam is gun mounted on X and Z axis. Again, then after that, Siaki, Pro beam and X beam are the major player in the market for the electron beam based wire beam additive manufacturing systems. One can also notice that the same electron beam gun can be used for metallurgical analysis of the build part in a different way. So the electron beam gun which you are using for depositing the material maybe can be used for analyzing the metallurgical properties. So now in the next lecture we shall discuss about the laser based wire beam additive manufacturing system. Thank you very much.